Welcome back. Hope you're doing well. Today we're going to be talking about eigenvectors again, but this time we're going to discuss the subset of problems that we were looking at previously where there was a basis of eigenvectors. Namely, we're going to be trying to figure out when we know how to put a problem into this category. When is it the case that the eigenvectors that we generate from a particular matrix operation give us a basis for our vector space? Let's go back to one of our examples from the previous week to kind of get used to and see what this sort of thing is talking about. Let's go back to the example on slide 4 of section 4.2. Here I have a little bit of a brief summary of what this one was. This one began with let L taking a vector x to the matrix of x, multiplication on the left by the matrix 0, 1, 1, 0 for that vector x, be a linear operator on R squared. And our task for this was a couple of fold. We were first trying to figure out how to write this in terms of a in regards to a particular matrix operator, but this time in terms of a basis of eigenvectors. Well, first things first, we had to go through and find the eigenvectors of this one. You may recall that during our geometry discussion that this matrix here is just flipping the x and the y direction. So if you have the y direction here, then that one's going to become the x direction. The x direction becomes the y. So that is how our matrix there is formed. In particular, when we think about it, there are two eigenvectors here, one of which is going to be the vector along the line y equals x, which is not affected by this flip at all. And then one is going to be the vector negative 1, 1, which is affected by it because it actually flips it to the opposite side of the line y equals x. Is this line being perpendicular to the line y equals x means that it just comes and flips straight across. It doesn't have any particular angle to it. It's a full 180 degrees. So V1 and V2 ended up being our eigenvectors for this operator L. V1 had an eigenvalue of 1 because it did not change its direction after going through L. And then V2 had an eigenvalue of negative 1 because it flipped its direction when we went through there. But it's in particular useful for us here, useful information that V1 and V2 form a basis for R2. We saw in some of our examples at the end of last week that not all particular eigenvectors actually form a basis. In fact, sometimes you have no eigenvectors at all, and sometimes you have an infinite dimensional vector space where it's very hard to be thinking about where these things have basis from. For example, you could get finitely many eigenvectors, as we saw in some of our differential operator type examples. But V1 and V2 here formed a basis for R2. In fact, we discussed that the matrix of L with respect to this basis of V1 and V2 looks like this, 1, 0, 0, negative 1. It was a diagonal matrix. So 1 meant that anytime that you plug in a multiple of the first vector here, 1, 1, you just get that vector back. That's all you have to do to get that. And then the negative 1 here meant that anytime that you plugged in a scalar multiple of V2, you got back V2, but with a negative sign out front of it, the negative being contributed by this negative 1 in front of this second diagonal entry. So you can see here that we convinced ourselves that these were the eigenvalues of this matrix, but this was only with respect to this particular basis. Remember that we said that in order for us to be able to actually figure out, okay, how does this matrix work for us, or like how does this connect back to our original matrix up here, was that we had to consider the transition matrix. We said let U be the transition matrix of something going from, say, E1, or rather, I think we would usually say it was from V1 and V2 all the way to E1 and E2. So this would be our transition matrix here. Then the way to write the actual matrix of transformation with respect to our standard basis of matrix, which, by the way, should be our 0, 1, 1, 0 again, was to form this transition matrix 1, and then 2, do the following composition. We would have, this is related to A, V1, and V2 right here in the middle, and then we would write U inverse. Yep, that's right. Just have to get my directions correct on the right of it, and then U on the left of it. Essentially, you're taking elements here from E1 and E2. So E1 and E2 elements come from inside here. So let me show it to you here. If I could write some sort of A times E1 plus B times E2 plus, once I put it through the transition matrix U inverse, it's going to take me to something in terms of coordinates of V1 and V2. Then this matrix is going to operate in terms of V1 and V2. And then finally, the matrix U would bring me right back to something in terms of E1 and E2. So we had to do a little bit of a transformation to make that happen. We had to multiply both sides by the, one transition matrix and then one inverse of that transition matrix. So the reason that we were able to do this and begin with, right, is that we were able to form a basis for this R2. Otherwise, this matrix here becomes very difficult to form, because how are we going to write eigenvalues that go all the way down? We don't have enough eigenvectors to get us there. So in fact, that's going to be our discussion today, is how the pivot of our success here in order to write this diagonal matrix as a matrix of this transformation with respect to its basis of eigenvectors was that we had enough eigenvectors to span the space. Otherwise, this matrix is not something that we're able to form. We can't even talk about a matrix with respect to the basis of eigenvectors because the eigenvectors don't form a basis. So that's what we had in this previous theorem, you may recall. Whenever you have a finite dimensional vector space, L is a linear operator on it. Whenever you have a basis for V and A is the matrix of the operator L with respect to that basis, we said that that matrix A was a diagonal matrix like the one we saw in the previous example, if and only if the vectors V1 through Vn are eigenvectors of L. And if that was the case, then the diagonal entries of matrix A are the corresponding eigenvalues of L. So we had to have had enough eigenvectors to fill up this space for this finite dimensional vector space. These eigenvectors, as we see up here, had to be a basis for V in order for us to even talk about things in this theorem. In particular, when we don't have a basis, so this is going beyond the theorem now, when we don't have a basis, we can't talk about a matrix of an operator with respect to, well, the collection of vectors that we have. That doesn't work. So we really like to be looking at these diagonal matrices for a reason that we'll see later on in this presentation. But in particular, the question of when you get diagonal matrices when you try and transform something into a matrix of an operator like this is a very interesting one. And it's one that we want to try and discuss a little bit today. So let's go ahead and look at this theorem that we already saw from before. If you have these k eigenvectors of a linear operator associated with distinct eigenvalues, lambda 1 through lambda k, so here all of our eigenvalues are distinct, then v1 through vk are linearly independent. So this kind of led us to one of our corollaries you remember from last time, where if you have an n by n matrix that you're working with, or just an n-dimensional vector space, and you're able to find n distinct eigenvalues, well, then you automatically get that your eigenvectors form a basis, because each one is linearly independent, and hence it's a maximal linearly independent set. A corollary of this is that if you have eigenvalues here, and if you associate to each eigenvalue its eigenspace, then these bases are disjoint, and the union of each of these bases that you get for the eigenspaces is a linearly independent set. So this is extending from the fact that if you take each of these eigenvectors here and even consider each eigenspace to have its own basis in there, even if it's more than one element, you still get that everything altogether is a linearly independent set. The reason that this comes from this theorem is that you could just pick a vector from each of the bases on each of these sets. Well, they all come from distinct eigenvalues, and hence they're all linearly independent. And since those choices were arbitrary, the whole thing must be a linearly independent set. Moreover, if the vector space V admits a basis consisting of eigenvectors of L, then S is exactly what we were looking for. If the vector space V has enough eigenvectors to form a basis, then S is that basis. This is the way that we would form it. We would just find all the eigenvalues, list all of our eigenvectors that make this work, and if there is such a basis of eigenvectors, then we have enough right there. That just tells us that we have enough to make a basis. And then finally, here is our n-distinct roots corollary that says not only, by the way, that the basis of Rn consists of eigenvectors of A, so you get a basis from that, but also you get that the eigenspaces are all one-dimensional. There's no room to fit anymore. You can't have two eigenvectors inside for one eigenvalue because you have n-distinct roots in an n-dimensional vector space. So there's no room to fit an extra one. So this gets us to knowing when we can do what is known as diagonalization of an operator. This might be something that you're familiar with. You may have seen this in a way of talking about A equals U, B, U inverse in the past. We would say, for example, the matrices A and B are similar in this case. And we would say in this case that A is diagonalizable if you could say that A is similar to the matrix B when B is a diagonal matrix. In particular, U needs to be an invertible matrix in order for this to be formed. So that is our restriction on that as well. Here is our theorem here. Let L be a linear operator on a finite dimensional vector space, and the following are equivalent. The matrix of L with respect to some basis is diagonal, and furthermore, there exists a basis for V formed by eigenvectors of L. So this is an interesting way of thinking of it. We have linear operators as helping us determine when operators are diagonalizable. Of course, we want to go beyond just the notion of matrices. So we're going beyond this framework here, hence why we're saying that these two conditions are equivalent. The first one being the matrix of L with respect to some basis is diagonal, and two, there exists a basis for V formed by eigenvectors of L. So that's what we mean for an operator L to be diagonalizable. In the space of matrices, though, this is exactly what formula that we have. A equals UB U inverse, where B is diagonal. This is the matrix of a diagonalizable operator. And, of course, by our previous theorem, that gives us a basis formed by the eigenvectors of A. So we can be writing these operators in a very neat way. So this was when we say matrices are diagonalizable. Let's see this in an example that we've seen before, like 2, 1, 1, 2. This one, remember, had two eigenvalues. We can stop right there. It's a 2 by 2 matrix, so it's working on Rn, where n is equal to 2, and it has two eigenvalues. The dimension is 2, the eigenvalues are 2. We already know that this is going to be a diagonalizable operator because there exists a basis of eigenvectors for it from our previous theorems. The eigenspace of A is associated to eigenvalue of 1, remember, was this vector, and the eigenvalue of 3. So this line spanned by 1, 1. And these two eigenvectors form a basis of R2 because they must. They are linearly independent. All right. Thus, the matrix A is diagonalizable. When we went through and did this work, we went and found these functions that we were looking at. U, you may remember, was our transition matrix. This was our transition matrix for this operator. You can see here what happens here is that once I found that transition matrix, that is just going to be where each of the columns of the matrix is each of the eigenvectors respectively. So that's how we were able to form that. And then B was the list of all the eigenvectors going on down the way. This is lambda 1, this is lambda 2, and then this vector here, this is V1 and V2. And then once we go through and calculate, we can see that A is indeed UB U inverse. Once we calculate all of that, we see that A and B are similar matrices. B is diagonal, and A is the matrix of our operator that we're working with, namely the 2, 1, 1, 2 that we saw previously. So here we see that the matrix A is diagonalizable. It can be made similar to a matrix B, where B is a diagonal matrix. Right. So this is one of the other ways that we could see that this is diagonal. We're just kind of going through the list and seeing that each of these are equivalent to try and convince us. Here's another interesting example. This one only had two eigenvalues, this time for a 3 by 3 matrix. So we can't immediately say that there's a basis of eigenvectors for this one, but we can start taking a look at what these eigenspaces are for each of these eigenvalues. For example, with the eigenspace of 0, we did get a one-dimensional vector space or an eigenspace for it. But for the eigenspace of 2, we got a two-dimensional vector space, an eigenspace that was of 2 dimensions. Well, let's count how many linearly independent elements we have then. Remember that V1 is going to be linear independent from both V2 and V3, as well as anything in the collection of those. So all of these are linearly independent from V1. V2 and V3 have to be linearly independent because it's a basis. So these three are all linearly independent vectors. Because of this, this is a union of these two bases of eigenspaces, which from a previous theorem we also know is just a linearly independent set. Hence, it is a basis for R3 since it has 3 elements in it. So this tells us automatically that this matrix A is diagonalizable. And if we take these eigenvalues, how do we form a diagonal matrix out of it? Well, here we go. We have an eigenspace of 0 for our first eigenvalue. So you can see here that we write lambda of 1 is 0 here. And then lambda of 2 is 2. And then and then 2 is also repeated down here, and that's because we needed a second space to fill in for this diagonal operator. Both of the vectors V2 and V3 have an eigenvalue of 2 associated to them, so each one gets its own space. And then for U, we just again repeated our vectors as columns of this matrix U, this transition matrix that we were working with. V1, V2, V3, you can see are all the columns of this matrix respectively. And now we can go through and claim that A equals UB U inverse. If we want to do the calculation, that's fine. But we also know, thanks to our theorems, that it's all based off of the other things that we already know about this operator. Now, to diagonalize an n by n matrix A is to find this diagonal matrix and an invertible matrix U such that you get this equation. So let's walk this through. Let's see us make this sort of thing happen. Let's do it with this example of A equals 4, 3, 0, 1 right here. So first things first, how do we make this work from the beginning to the end? Here is our matrix. We're going to start by trying to find eigenvalues and eigenvectors for this matrix. Here, we're going to start by the characteristic polynomial, the determinant of A minus lambda I, which once I go through and calculate, it turns out it's just 4 minus lambda times 1 minus lambda. The off diagonals multiply to give us 0. That one's an easy one to factor. We know that the lambda values for this one are 4 and 1, and hence the associated eigenvectors. And once I go through and find out what those are by calculating, just like we did in the previous video, are V1 and V2 being 1, 0 and negative 1, 1, respectively. Well, this gives us everything that we need. We have our diagonal operator, which you can see I'm associating each eigenvalue with the vector that it's associated with. That order is important. If I switch V1 and V2, that does not work. So this is my lambda 1, and this is my V1. Lambda 1 goes in my first row, first column, and then V1 is my first column vector for U. Similarly, lambda 2 is my second row, second column for B. And then finally, V2 is our column vector for U, our second column vector there. So this is how we can walk from the beginning to end to talk about this diagonalization. It is just finding eigenvalues and eigenvectors. This one, we didn't have to ask the question, is it diagonalizable? At least it was answered very quickly because we have two eigenvalues and we're in a 2 by 2 space. Now, two obstructions do hold with this. One is we might go through and realize that when we write how many eigenvalues there are, first, there are less than n being the dimension of our space, because at that point, we start having to ask the question, do these vectors really form a basis for my space? But really what we have to do in order to determine that is just count. For example, here in our case of A equals 1, 1, 0, 1, if we go through and form this basis here, or rather this characteristic polynomial, we get lambda minus 1 squared. So we get one eigenvalue that raises our question, do these eigenvectors actually form a basis? Once I go through and solve this equation, the associated eigenspace only has one eigenvector to it, 1, 0. Because of this, I know that I only have one vector, but I have a two-dimensional vector space. That tells me I do not have enough eigenvectors. So I do not have enough eigenvectors to get a basis for my space. Example 2, on the other hand, tells us, okay, well, what if we had this matrix here, A equals 0, negative 1, 1, 0. Remember, this is the one that's a rotation by 90 degrees. Remember that we said in this particular matrix that looking at eigenvalues and eigenvectors was going to be difficult if we were in the real numbers because, and we can see it here, its characteristic polynomial is lambda squared plus 1. Attempting to set this equal to 0 gives us lambda equals plus or minus I, the imaginary number. So no real eigenvalues or eigenvectors even exist for this. So one other issue is that you could just run out of eigenvalues in total. You might have no eigenvectors at all, or eigenvalues at all, and hence no eigenvectors to go with them. However, for this one, there are complex eigenvalues and eigenvectors. And in our next video, we'll talk a little bit about how we can be treating those and how we can look through things in the lens of thinking of this as a complex vector field rather than a real vector field, namely one where the scalar field that we're working with includes the number I. But for now, when looking at the real line, these are the two obstructions to finding a basis consisting of eigenvectors. This can be either you have eigenvalues, but there's just not enough eigenvectors, or you run out of eigenvalues total. So let's say that we have a problem that involves a square matrix A in the context of matrix multiplication. Well, let's say, for example, we want to go through and do multiplication with diagonal matrices. One particular eigenmatrix, or the operations with diagonal matrices can look pretty nice. For example, let's say I wanted to go through and multiply these two diagonal matrices together, 2, 0, 0, 3 and 4, 0, 0, 5. Well, how would I multiply these together? Well, I'd just do the same thing as I normally do with matrix multiplication. So I go through and multiply 2 times 4. It gives me 8 on the top left. 2 times 0, 0 times 5. 2 times 0 is 0. 0 times 5 is 0. So I get 0 here. I'd similarly get 0 on the bottom left. And on the bottom right, I would get 0 times 0 plus 3 times 5. I'd get 15. Notice that each diagonal entry just multiplied across. 2 times 4 is 8. 3 times 5 is 15. In fact, this is a really neat thing about diagonal matrices, is that when you have zeros everywhere except the diagonal, then multiplying these sorts of matrices becomes so much easier because you just get so many zeros in your calculations. The only ones that are non-zero are the ones in which you have diagonal entries where they are non-zero. So this ends up being very nice. In particular, let's say that I have a diagonal matrix and I want to find the power of a diagonal matrix. This ends up being very useful, say, if you want to take a Taylor series of a particular matrix. Now, this sounds a little crazy, but you can do this. And this is a very neat way to get to do that. If you're trying to take powers of a matrix over and over again, then this ends up being a very useful tool, is to know that we have a diagonal matrix, or that at least our matrix is diagonalizable, because now if we can write this matrix A in this diagonal format, then we know that in order to take a power of A, we just write each diagonal entry to the power of K. Everything else remains 0. That's an awesome, awesome calculation. Big fan of it. So for example, let's say right here, we have A equals 4301, and we want to find A to the 5th. This was our example from a couple of slides ago. Well, we know that A can be written in terms of the following way. A equals UBU inverse, where B is this diagonal matrix. This is going through and calculating our eigenvalues for this. And U is our transition matrix consisting of eigenvectors. So we have B, we have U, and hence A to the 5th equals UBU inverse times UBU inverse times UBU inverse times UBU inverse times UBU inverse. I've just multiplied this through 5 times. Now, what can we do now? Remember that matrix multiplication is associative. I don't even need parentheses here to talk about what I'm doing here. I can take U inverse and U and say, what is that? Well, if you multiply any matrix times its inverse, this is just the identity. Same thing right here. This is just the identity. This is just the identity. Everything that has a U inverse and U inside of it multiplies to give me the identity. Once I'm done with that, what am I left with? I have one copy of U on the left, and I have, let's see, I'll count them here. 1, 2, 3, 4, 5 copies of B. That should make sense because we needed 5 copies of A. So that's B to the 5th times how many U inverses do we have? Well, just here at the end. So when I go through and calculate all of that, I get U times B to the 5th times U inverse. This is a much simpler calculation because now I'm just taking the power of a diagonal matrix. B to the 5th is going to give me 1024 in the top left and 1 in the bottom right. And then I just have to multiply U on the left, U inverse on the right. Once I do that, I will get this matrix right here. So finding the power of a in a diagonalizable matrix ends up being awesome. It is so good because we can just write this in terms of its eigenvalues and eigenvectors, write it as similar to a diagonal matrix, and then taking a power in this place is excellent because we can start canceling out a bunch of terms that end up being inverses of each other on the inside here. So this ends up being a very, very excellent tool for us to use in this problem. We could even do this for any power now, can't we? We can actually get a little bit of a trick in here. If A is a diagonalizable matrix, we could find A to the power of K. We could do this for any power now. Again, this is very useful. Sometimes you need to find multiple powers if you're ever doing, say, a Taylor series with respect to this particular matrix. Well, we know that A equals UBU inverse. We can write the same stuff as before. Then the same formula happens, except we're taking out taking out 5 as our power and plugging in the arbitrary power of K. So this is U times BK times U inverse. We write everything out and we write in what B to the K is. It's going to be 4 to the K, and then 1 to the K in the bottom right, but 1 to the K is just 1. And then you can go through and calculate this with just 4 to the K as having its variable K inside of there. And then you can check to see that this general formula matches up to our expression that we went through when K was equal to 5. So this is a really neat tool. This tool is one that says that I can take any power of a matrix A, and as long as A can be written in form of UBU inverse then writing this to the power of k is just going to give me u times b to the k times u inverse. And if this is an easier matrix to take a power of, like a diagonal matrix, then the calculation is so much more simple than just multiplying the matrix over and over and over again. So we've gotten some idea of why we might want to do things in a diagonalizable way. Let's keep going through some applications here by looking at this initial value problem for this system of linear ODE. So let's take a look at this ordinary differential equation. You see here we have notation for the derivative of x with respect to a parameter t, as well as with respect to y with respect to parameter t. So this is an ordinary differential equation. We have a way to solve for x and y in terms of one variable t. Notice it is a system of equations we're solving for, though. We would like to solve for x and y at the same time, because you can see here, dx dt, for example, is written in terms of both x and y. We're even given initial conditions to help us make sure that we are not ending our answer with any of our arbitrary constants and things like this. Now, why are matrices going to be useful for us here? It's a very good question. Notice on this left-hand side that we're in some sense taking a differential operator here. We are taking, namely, the derivative of a vector v with respect to t. Here, v is our vector xy. V is our vector xy here. And if we take that derivative of the vector with respect to time, then what we get back is a times the vector back again. So v, again, is our x and y. So this is our column vector here. We are writing this as 4 times x plus 3 times y. 4 times x plus 3 times y. If I write xy as my column vector down here, then 4 and 3 go right here. If I do this matrix multiplication, I get 4x plus 3y. And so because of that, there is this way of writing this as a matrix operation. dv dt is multiplying on the left by this matrix 4, 3 for the first equation. And then on the second equation, it's no x times plus 1y. So 0x plus 1y. So we get a matrix operator here. Here is that matrix operator, and here is our vector v. Very interesting, because now we can start applying some of the things that we know about linear equations, right? Linear matrix transformations for this sort of stuff. Now the matrix A is diagonalizable. We've seen this one already. We can write this in terms of its eigenvalues and eigenvectors given right here and right here. So what's going to happen here? Why does it help us to write this in terms of a diagonalizable matrix? First, let's see what this equation would turn into as we diagonalize this matrix. What we're about to do is apply a change of variables. When we would integrate, we would sometimes do this with u substitution in order to make the integral a lot easier to manage. In this one, we're going to do a change of variables to make this ordinary differential equation much easier to manage. Let's write w equals w1, w2 as the vector v relative to our new basis, relative to the vector given by v1 and v2, the eigenvectors of A. Then we can write the vector v in terms of the transition matrix given by u, this transition matrix given here. Remember, u takes us from the new basis back into the old basis. What that means is that we can actually just take u inverse of both sides and write our old basis elements, v, in terms of w by just applying u inverse here. Okay. So this is going to be part of our change of variables. Our variables now are no longer going to be x and y that we're going to be solving for. We're going to try and solve for w1 and w2. Let's see how this map is going to go. We're going to have things with respect to our original basis. So let me see. How do I want to call this? Let's call this Let's call this R2, and what I'm going to do is I'm going to specify what vector elements that I'm looking at right here. So V1 and V2 is what I'm looking at, and then here is our matrix operator A that we're writing with, R2, now written in terms of V1 and V2 again. But we are going to apply an operator, which is going to be U, in order to get us from the new basis to the old basis. When we would do that, we would write it like this. Here's R2 with respect to U1 and U2. And this is our matrix U. Same thing right here. We're going to have this stuff to work with right here. Okay, and this is going to be our matrix U again. We would like to know more about this operator, this space that happens right here. Essentially, how do we rewrite A so that we are working with, instead of A here, we're working with a diagonal matrix B. We would like this to be our diagonal matrix B. Well, in order to go through and calculate that, we've got all of our formula stuff ready to go. We've got our map and everything. So in order to form the matrix A, it looks like it's going to be something like this, right? It's going to be something like U inverse, B, and U, something like this. And indeed, it is the opposite direction. No, it's not. That's the right direction. Sometimes I have to get my direction stuff sorted exactly. So if I'm solving for B, which is what I would like to have here, then I would write that B is equal to apply U inverse to both sides to get U inverse A, and then apply U to both sides and get U inverse A U is equal to B. And that's exactly what we have right here. Here we have a new formula to go through and solve. dW dt is applying this to U inverse of V. Well, U inverse is just a matrix full of coefficients. It's just full of constants with respect to the variable t, so it can be moved outside the derivative, which is a linear operator. So U inverse can be brought outside. We know dV dt is AV, right? This is this matrix of multiplication here. And finally, AV can be written back in terms of the vector W, which is V is UW. That's from our formula that we had up above. So there's the connection that what we're having. We did two connections at once, so let's spell those out very briefly. The first one that we did was we made sure that we connected back what it meant for A and B to be related. Namely, B is a diagonal operator that seems to be easier to be working with, but we'd like to go ahead and make sure that we're coming back to our source of A, that we're able to recover the matrix A that we were originally working with, namely 4, 3, 0, 1. So we did this making sure that we kept all of our operator stuff correctly. Now, we did go ahead and make this change of variables where the vector V is U times the vector W. And what we'd like to do is write this matrix operation now in terms of this new basis, the basis of V1 and V2. Let's see what that looks like here. In order to do this, we wrote dW dt right here. This is the new basis that we're taking our derivative with respect to t. And we'd like to figure out, okay, what is that? Well, right now it's not in the correct basis. It's got to be written in terms of v for me to write what this basis is. So I write W as U inverse of v. So that's the connection that we're making here. This is U inverse of V, so that's the connection there. U inverse is linear, so we can take it outside. That's this part right here. And now we have dV dt. That's the thing that we know is equal to A times V. And finally, to get this back to the vector V, we write V as UW, which it is. So now we have this formula, dW dt equals B times W. Why is this better? Take a look at what we have. We now have a system of ODEs that is easy to solve. There's no intersplicing of the variables in the two equations here. I don't have a W2 inside of my first equation anymore. It's just W1. So now I can go through and do the exact same formula stuff that I would do previously, integrate both sides of dW1 divided by W1 and of 4dt. And I would get that I have a general solution from W1 of a constant times e to the 4t. Similarly, W2 would be constant sub 2 times e to the t. So I have general formulas for each of these two equations now. Now, using the initial condition is a bit tricky because, again, the initial condition is written in terms of the vectors v. So we need to get those to be in terms of the vector w as well. So right now, let's go back real quick and check our original initial conditions. Our initial conditions are currently telling us x0 equals 1, y0 equals 1. Well, here's our vector xy. So this is really just plugging in 0 for t inside of the vector v. And we know that v0 is equal to 1, 1. So that's the vector that we get from that. So now we're back here. That's our vector. v0 is 1, 1. That's this guy right here. And we'd like to write that in terms of w, because that's what we have our initial conditions for. So we write w0 equals u inverse of v0. Well, here's u again, and we're going to invert it before multiplying. And that's going to get us 2, 1 as our vector here. This is, again, our initial conditions for what 2 and 1 should be. That is, whenever I plug in 0 for t here, I should get 2. Well, if I plug in 0 for t, I get C1 times 1. That's equal to 2, so C2 is going to be equal to 2. Similarly, C1 is going to be equal to 1, so you see I have a constant out here for W2, the constant for e to the t, the general solution I got from that. So finally, I've got everything that I need, except I want to write it back in my original basis. I'm currently in my change of variables stage. So I'd like to write that back in terms of V, but remember that V is equal to U times W, which is this formula right here. So here's U, here's V, and writing it all together, that gets us our answer. So diagonalization can actually save us time in solving differential equations. Instead of having to get all mixed up in all these different variables, what we're doing here is doing a change of variables to help us solve this out. So eigenvalues and eigenvectors can be extremely useful in this context. Now, we know that one of the issues that we have in trying to get diagonalization to work is that sometimes the multiplicity of lambda inside of the characteristic polynomial does not add up to the number of eigenvalues that you have. For example, you could have a characteristic polynomial. We had this one, for example. I think it was something like 1 minus lambda to the 4. So you can have a characteristic polynomial like this, where lambda equals 1 has multiplicity 4 in this equation. So it has multiplicity 4, but if you remember, again, I don't recall where this example was, but it was somewhere back in our notes. If you recall, we only got one eigenvector for that. So sometimes the multiplicity of lambda equals 1 in our characteristic polynomial does not match up with something called the geometric multiplicity of lambda. We'll define the geometric multiplicity of lambda to be the dimension of the associated eigenspace. Essentially, if you have only one eigenvector for a multiplicity 4, then that's still a geometric multiplicity of 1, even though your algebraic multiplicity is 4. So if the two don't line up, that gives us an issue. That means that we are not able to diagonalize our matrix. So again, sometimes we'll call the algebraic multiplicity the eigenvalue of the multiplicity of this eigenvalue to be the multiplicity as a root of the characteristic polynomial of n. So sometimes we might call this an algebraic multiplicity. This root appears 4 times when it's completely factored. Then the geometric multiplicity of lambda is the dimension of the eigenspace, which could be a geometric multiplicity of 1. That could happen even if your multiplicity is 4. Okay. Now, there is one thing that is clear here, which is that if you have a multiplicity of 4, you can only have at most 4 linearly independent eigenvectors. There's no more that you can find. That's exactly what this theorem is saying. That geometric multiplicity of an eigenvalue cannot be bigger than the algebraic multiplicity. So that's what this theorem is all about. So we often want to use this as our test of diagonalization. If we want to see if something is diagonalizable, we'll usually just say, okay, if it's something that's got an eigenvalue of multiplicity 1, we won't fool with it. We already know it's got an eigenvector. That's not going to hinder us in saying whether or not this is diagonalizable. What we'll do is we'll look at the things that are of multiplicity 4 or 2 or more, really. And that'll be one of the factors here for a test of a diagonalization. In fact, a real square matrix is diagonalizable if and only if the following things are satisfied. First things first, characteristic polynomial needs to split into factors of degree 1. You can't have any complex roots. If you have complex roots, you're losing eigenvalues. So having complex roots means not diagonalizable. At least it's not diagonalizable. See if I can write it here. There we go. It's not diagonalizable in the real sense. That is, working with the real vector fields. Again, next time we'll be talking about complex vector fields, and we might have a different conclusion there. But that's the first one there, is that characteristic polynomial splits into factors of degree 1. And the second one is that the geometric multiplicity equals the algebraic multiplicity. We already know that if algebraic multiplicity is 1, geometric multiplicity is 1, so we don't need to check those. But if the algebraic multiplicity is 2, we need to see if we can get 2 linearly independent eigenvectors that share that eigenvalue. So that is our test for diagonalization. So here are those tests once again. Again, this is for linear operators over R. This first one shouldn't be too much of a stretch from what we were just discussing. The characteristic polynomial, which works nicely if we're working with a finite dimensional vector space. So this should be thought of as what that is. It splits into factors of degree 1. That is, all eigenvalues of A are real, and the geometric multiplicity and the algebraic multiplicity are the same. And then linear operator L on an n-dimensional vector space, V, is diagonalizable if and only if the following conditions are satisfied. All eigenvalues of L are real. That's the first point again. And we're going to see this again, but this time with the second point. For each eigenvalue lambda of L, the algebraic multiplicity of lambda equals this. This is interesting, isn't it? So now we're able to talk about geometric multiplicity in a different way. In this first way, we were saying, okay, we need to go through and find however many linear and independent eigenvectors we're able to get. Well, how many does that need to be? For each eigenvalue lambda of L, we want to get the algebraic multiplicity of lambda to be equal to this value right here. This is n minus the dimension of the column space of L minus lambda I. Remember that L minus lambda I does have some sort of null space going on here, right? Remember that this is equal to, since we're looking at n-dimensional columns here, and we're working on just checking something real quick. Yeah, we're working on matrices here. Then this is equal to the dimension of the null space of L minus lambda I. Dimension of the null space would be all of those values at which you get an eigenvector for. Namely, it would, if you try and plug that into this equation, then that this times b would equal 0, the 0 vector in your space, because that would be an eigenvector. So you want the dimension of that null space to be what this is. In order to calculate the dimension of the null space, we just take n minus the rank. The easy reason is that we can calculate rank. We can calculate rank by doing row operations on the matrix, figuring out how many pivot columns it has after row reducing it. So that is a neat little test that we could be using here as well. Let's see this here in an example. Let's go ahead and write down an example here using test 2. So let's check it out with this example. Here we go. We've got test the matrix. This matrix is going to be A equals 3, 1, 0, 0, 3, 0, 0, 0, 4. Let's test this matrix for diagonalizability. Nice big word there. Let's test this matrix for diagonalizability. So first things first, I can't just apply row reducing stuff to this matrix yet, because if I did that, I would look at this and I'd immediately say, oh, well, look at that. This is row reducing equivalent to a diagonal matrix, therefore it's diagonal. That does not work. We need to go through and find, thanks to this test here, we know it's an if and only if, we need to go through and find eigenvalues and eigenvectors for this matrix. Well, to do this, I'm going to first start by forming what is A minus lambda I. Well, I'm just going to be taking the diagonal entries and subtracting lambda, or minus lambda here. And in fact, we might notice that this is an upper triangular matrix, so figuring out what this characteristic polynomial is going to be very nice. The determinant of this matrix is going to be 3 minus lambda squared times 4 minus lambda. 3 minus lambda squared times 4 minus lambda. Well, that gives us two roots. We have that lambda equals 3 is a eigenvalue with algebraic multiplicity of 2. I'll use AM for algebraic multiplicity, whereas lambda equals 4 is an eigenvalue of algebraic multiplicity 1. Well, we don't have to worry about this one. We do not have to worry about lambda equals 4 because we know that its geometric multiplicity also must be at least 1. Otherwise, 4 would not be an eigenvalue. So because of this, that's not one we have to worry about in our test for our diagonalization. We do need to check to see what the rank of this matrix is after we plug in 3. So let's see what that ends up being. What happens to this matrix if we end up plugging in 3? Let's see if we can calculate what its rank is. Well, I've got this matrix here. I'm going to take every diagonal entry and just plug in 3 for lambda. So I should get 0, 0, 1. And I'm just going to copy down the rest of this matrix. Should get something like this. Now, I don't have to do much. I can just swip the second and third rows, and I'm already in reduced row echelon form. That gives me what my rank is. My rank for this matrix is going to be what? I'm going to have 2 pivot columns, right? One right here. And then eventually, once this comes up, one right here. Because of this, I should have a rank of 2. Now, calculating the geometric multiplicity for this involves calculating what is n minus the rank of A minus 3i. Well, that's going to be 3 minus 2, right? Because we're working on 3 by 3 matrices. So this is going to give me, see if I can write this here. Maybe not. I can try. This is going to give me 1. So that's going to give me 1 as this geometric one. So here, I can calculate the geometric multiplicity here to be 1. I look at these two numbers, I see they do not match, and I say that this matrix is not diagonalizable. Oops, diagonalizable. And that's because we found an eigenvalue that did not have a geometric multiplicity equal to its algebraic multiplicity. Namely, if I went through and tried to find vectors that spanned this null space, I'd only find 1. I would only find 1. And so that is the story of that. In fact, I think x1 is your free variable here. I think you're forced to say that x2 and x3 are both 0 in that. So it should all be spanned by 1, 0, 0. You only have one vector inside of your eigenspace, and you need 2 in order to match the algebraic multiplicity. Hence, this matrix is not diagonalizable. So it doesn't have many of the nice properties of what we were seeing before. All right, checking my notes, make sure all of this is good. It does look good to me. So what we talked about today is that diagonalization. What it does is it makes operations nicer whenever we are multiplying matrices or working with matrices, either in the case of making powers of them or also in using them for ordinary differential equations. Not all matrices are diagonalizable, however, even ones that have, full rank and things like this. So we needed to talk a little bit about when that happens. Well, it happens whenever you have a basis of eigenvectors. So that's what we've gone through and calculated. We talked about algebraic versus geometric multiplicity, and how the comparison or lack thereof of these numbers can be a good test for diagonalizability of a matrix operator. But that will do it for me today. Thank you so much. Have a wonderful day.